Good evening, everyone, and welcome to day 2 of our 10-day short course program on metrology and mechanical measurement. Today's session is focused on an essential foundation of engineering measurements, units, and systems. I'm very much pleased to take you through this important topic for today's short course program. The central message of today's session is simple: measure accurately, engineer precisely, and excel consistently. In engineering, precision begins with understanding what we measure, how we express it, and which system of units we use. So, in this session, we will understand the fundamental concepts of measurement, units, and systems, and their importance in engineering and metrology. Our discussions will cover fundamental and derived units, the SI system, different systems of measurement, unit conversion, and dimensional consistency. Let us first look at today's roadmap. We will begin with fundamental and derived units. Next, we will study the international system of units and its 7 base units. Then we will compare the CGS, MKS, FPS, and SI systems. After that, we will learn a reliable method for unit conversions. Finally, we will discuss dimensional consistency and dimensional analysis, which provide a powerful method for checking engineering equations. Why measurement matters in engineering? Why is measurement so important? Almost every engineering decision depends on measurement. Whether we are machining a component, inspecting a product, designing a machine, or certifying a structure, we depend on measured values. But a number by itself does not provide sufficient information. For example, if someone says the value is 20, we must immediately ask 20 is what? Is it millimeter, 20 inches? Is it 20 millimeter? Is it 20 inches, 20 kilogram, or 20 seconds? Therefore, a measurement without a defined unit has no complete engineering meaning. When we say 20 millimeter, the value becomes more precise, reproducible, and understandable globally. Standard units allow engineers, scientists, and industries to communicate measurement results clearly and consistently. Now let us understand the difference between fundamental units and derived units. Fundamental or base units are independent units. They form the foundation from which other units are constructed. Examples include length is measured in meters, represented by m. Unit for mass is kilogram, represented by kg. The unit for time is second, represented by s. Unit for electric current is ampere, represented by A. And finally, for temperature, the unit is Kelvin, represented by K. The derived units, on the other hand, are obtained by combining fundamental units according to physical relationship. For example, area is expressed as square meter, velocity is expressed as meter per second, force is measured in newtons, where 1 newton is equal to kilogram meter per second square. Pressure is measured in pascals and energy is measured in joules. Understanding this relationship is essential because derived quantities ultimately depend on fundamental quantities. Now let us move to SI system of units. SI stands for International System of Units. The SI system provides a coherent and internationally recognized framework for measurement. The 7 SI base units are meter for length, kilogram for mass, second for time, ampere for electric current, Kelvin for thermodynamic temperature, mole for amount of substance, and candela for luminous intensity. All other SI units can be expressed as combinations of these seven base units. The SI system therefore provides the foundation for standardized and traceable measurement in modern science, engineering, and industry. Engineer may encounter different systems of measurement. The first is a CGS system, meaning centimeter, gram, and second. Second is MKS system, which refer to meter, kilogram, and second. Third is FPS system, foot, pound, and second. And finally, we have SI system, which is internationally adopted standard. The MKS system forms an important foundation for the modern SI system, while FPS represents the imperial or British system. And an important practical point for engineer as follows. Always identify the measurement system before performing calculations. Mixing units from different systems without proper conversion can lead to serious measurement and calculation error. Let us now discuss the unit conversion. Unit conversion is a routine but extremely important engineering skill. A reliable technique is the factor label method, also known as the dimensional method. There are four basic steps. First, identify the given quantity and its existing unit. Second, select the appropriate conversion factor. Third, arrange the conversion factor so that the unwanted unit cancels. Fourth, perform the calculation and express the result in the required unit. Let us consider a simple example. Suppose we want to convert 5 kilometers into meters. We know that 1 kilometer equals 1000 meters. Therefore, 5 kilometers multiplied by 1000 meters divided by 1 kilometer give us 5000 meters. Notice that the kilometer unit gets cancelled, leaving meters as the final unit. Let us consider another example. To convert 100 degree Fahrenheit into degree Celsius. We use the following relationship. Celsius equals Fahrenheit minus 32 multiplied by 5 divided by 9. Therefore, 100 degree Fahrenheit is approximately equal to 37.8 degrees Celsius. Let us now review some of the commonly used conversion factors. 1 inch is equal to 25.4 millimeters. 1 foot equals 0.3048 meter. 1 mile equals 0.609 kilometers. For mass, 1 pound is approximately 0.4536 kilogram, while 1 kilogram is approximately 2.2046 pounds. 1 ton equals 1000 kilogram. For volume, 1 US gallon is approximately 3.785 liters and 1 liter equals 1000 cubic centimeters. For pressure, 1 atmosphere is approximately 101.325 kilopascals, while 1 bar equals 100 kilopascals. These values are useful reference values. However, in certified or legal metrology applications, the exact conversion factor required should always be confirmed. We now come to one of the most important powerful concepts in engineering, dimensional consistency. A physical equation is dimensionally consistent when both the sides of the equation reduce to the same combination of base dimensions. For example, consider the familiar equation. Force is equal to mass multiplied by acceleration. The dimension of force is represented as mass multiplied by length divided by time squared. Therefore, the above equation confirms the dimensional validity of the force relationship, as illustrated here. Dimensional analysis is always useful for verifying engineering formulas, detecting errors, deriving relationships, and converting consistently between systems of units. A useful rule to remember is if the dimensions on the two sides of an equation do not match, the equation cannot be physically correct. Let us now connect these basic concepts directly to metrology and mechanical measurements. Fundamentals of measurement units and systems integrated to metrology and mechanical measurement. The first one is calibration. Instruments such as calipers and micrometers are calibrated against appropriate standards with traceability to recognized measurement standards. Second is quality control. Consistent units make inspection results more comparable across machines, production shifts, and manufacturing facilities. Third is global trade. A component manufactured according to a specification in one country should produce the same measurement result when inspected in another country. Finally, there is design integrity. Dimensionally consistent equations help engineers to prevent costly design errors before manufacturing begins. Let us now quickly recap what we have learned today. First, the fundamental units are essentially independent, while derived units are constructed from them through physical relationship. Second thing, the SI system contains 7 base units that provide the foundation for scientific and engineering measurements. Third, engineers should understand the CGS, MKS, FPS, and SI system and identify the system being used before performing calculations. Fourth is the factor label method provides a systematic and reliable approach to unit conversion. And finally, dimensional consistency provide a quick and powerful method for checking the validity of engineering equations. So with this above conclusion, we have completed day 2 on measurements, units and systems. I hope this session has helped you to understand why units and measurement systems are fundamental to accurate engineering practice. Always remember one thing, a number becomes meaningful only when it is associated with a proper unit. And in engineering, precision is the foundation of engineering excellence. Thank you for participating in today's session. I look forward to seeing you in the next subsequent session of our short course program. Thank you all.